So we're discussing Simpsons rule, and Simpsons rule was developed by an English mathematician, Thomas Simpson. He lived in the early 1700s. So to kind of understand Simpson's rule, we need to go back to the trapezoidal rule. Now, let's review what we did for the trapezoidal rule. Say if we had a function here, it's the same function. And we're going from A to B. So we're going from A to B. A to B. And we're trying to approximate the area from A to B under the curve of f of x dx. And the idea is that it's approximately, in this case, let's just say T3, which would mean take our interval and split it or partition it into 3 subintervals. Okay. And then on these 3 subintervals, in fact, let me just erase this over here. On these 3 subintervals, essentially what we're doing is we are approximating the function by a bunch of line segments. So let's look here. So if we look at, so let me in fact just kind of erase. Let me zoom in here. If we erase, we can see that what we're doing is essentially saying, hey, look, let's use or let me use blue. That blue. Let's pretend our function looks like this. Right? So does that make sense to you that we're assuming that the function itself, in order to approximate the area under the curve, what we're doing is we're approximating the function. Do you get that? So instead of having something that's curvy, we're saying let's rewrite this curvy function and approximate it by a bunch of line segments that are grouped together. And then the more you increase, as you increase in, you're increasing the line segments that you can use to approximate your function. Okay? And so the idea is that it's easier to find the area under these line segments because that's just going to be the area of a bunch of trapezoids, right? That's going to be super easy to compute because we've got a really easy formula for that. And we've got this second trapezoid here and a third trapezoid here. Right? So Simpson's rule takes this idea and bumps it up.
It's 6:30.
And bumps up another level and says, instead of working with a bunch of line segments, why don't we work with a bunch of parabolas? Right? Copy, paste. So in working with a bunch of parabolas, this is the approach of, or the methodology behind Simpson's rule. So here's what we would do. We would say if we want parabolas, first of all, a parabola is determined by any 3 points. So just like a line is determined by 2 points, a line is determined by 2 points. What do we mean by that? We mean once you draw 2 points, I already know what line you're talking about, right? Because there's only one line that goes through those 2 points. So a line is determined by 2 points. And similarly, a triangle is determined, not a triangle, a parabola is determined by 3 points. So a parabola is determined by 3 points. So if you just draw any 3 points, I know what parabola you're talking about, because if you remember back from pre-calculus, we've got the directrix and the focus and all of that stuff, right? And we could also just say, okay, suppose we've got these 3 points on here. Maybe this point is x1 comma y1, x2 comma y2, x3 comma y3, right? If I've got a parabola as ax squared plus bx plus c, that's a general format for a parabola, right? General format for a parabola. So then x1, y1 has to satisfy this, right? So that means y1 better be equal to a x1 squared plus b x1 plus c, right? And then y2 also, x2, y2 has to satisfy this. So a x2 squared plus b x2 plus c has to be y2. And lastly, a x3 squared plus b x3 plus c better be equal to y3. So now I've got system of equations, right? 3 unknowns. The unknowns are a, b, and c. A, B, and C. So we've got 3 unknowns, 3 equations, right? And we can solve this system of equations for those 3 unknowns, A, B, and C. And once we know A, B, and C, bam, we know the equation that we're talking about. And let me actually point out that you might be thinking, oh, this is something radical, this is something new. Actually, it's not. If we have 2 points, right, and we say, okay, a line is determined by those 2 points. These points are x1, y1, x2, y2. Now, what's the general formula for a line? We can say ax plus b equals y, right? Or mx plus b, either way. Now, x1 has to satisfy this, x1, comma y1, and x2, comma y2. We have a system of equations, 2 unknowns, 2 equations, and solving this is the same as giving our formula for, there's a point slope formula for a line, and then there's a point intercept, and then there are 2 points, right? So the equation that, you know how there are 3 general formats for a line, right? This right here is the slope intercept. Well, we also have the point, right? And then the point slope. So the point formula or format for the equation of a line is derived from solving this system of equations with 2 unknowns and 2 equations. Okay, so that's 2 points, and then we can bump it up to 3 points, and we can get some kind of parabola. So say in this instance, this looks like a parabola that's facing downward. So maybe the parabola looks something like, something like that. I don't know. I would need to solve this system of equations in order to determine A, B, and C. Okay. So with Simpsons rule, the idea is to take our take our graph, and we're going to split it up. We're going to approximate the function by a bunch of parabolas. And each parabola requires 3 points to determine it. So if we have these kind of interlocking parabolas or parabolas that are connected to each other, let's see if we can try to do that. So say if we wanted to have a parabola, we would need to know, say, this point. Say we could form a parabola from, may as well take those 2 in the midpoint, right? So like get a parabola out of those three. And now to turn this middle third into a parabola, use this middle point here. We'll make a parabola out of these three. And then for this last third to turn it into a parabola, we can use the endpoints and the midpoint to get our third point. Okay, so I'm going to just kind of, I think it's kind of hard with this, but I can kind of see what might be, like this might be a parabola. Let me try to do that better. Yeah, so this might be a parabola. Okay. Now this parabola with the next three, it looks kind of intense. Let me change colors here. I would say this looks like we're coming down and like we're part of some really big parabola, if that even makes sense, right? Because those lines, the 3 points are so close to a line, like maybe the vertex of my parabola is down here somewhere. Okay, and then for the last three, I put a different color, maybe something green. Could be that this is a really steep parabola. So let me start down here. All right, so maybe it's kind of steep like that. So what I would do to get the area is I would want the area from here to here. I would use the area under that parabola, right? And then for my first third, right, because remember I took the subinterval. I took the interval AB and I had it split into three, remember? 3 subintervals. So like this is my first subinterval, my second subinterval, and my third subinterval. So for my first subinterval, I would need to use this much of the parabola. Okay, so or I think maybe I could have this kind of, yeah, that's better. My lines aren't that straight. And then I would have underneath here for my third subinterval. So you can see that we're getting, if we have a curvy graph, it's easy. Sorry, I have to blow my nose. Sorry about that. If our graph is curvy, then we're doing better approximations by using parabolas because the parabolas are curvy. And so the parabolas are better able to approximate the function, right? So the Simpsons rule is going to do, a good job, a better job than the trapezoidal rule or the midpoint rule because you have more flexibility because you can use a parabola to estimate your function as opposed to just being able to use line segments. So that's one thing I want to point out. Another thing I want to point out is that how many points did we need?